All right. Well, welcome everybody to another stream of Keenan Can Do Learning C# Programming. We last left off with finishing chapter 7, which was the integer types in C. We're gonna dig into chapter 8. Doesn't look like a very large chapter tonight on floating point types, and then move on to operator precedence in C, chapter 9, if we have time. I've also come across a few resources for practice problems, as well as in addition to the ones that ChatGPT has provided. So I look forward to sharing those as well. But without further ado, we'll jump into some floating point types, and begin the stream. So. In this chapter, we learn floating point basics, floating point constants, operators, conversion to and from integer types, the IEEE-754 floating point standard, round off errors, reading and writing floating point numbers, non-infinite numbers in C, the math library. Real numbers are represented in C by the floating point types float, double, and long double. Just as the integer types can't represent all integers because they fit in a bounded number of bytes, so also the floating point types can't represent all real numbers. The difference is that the integer types can represent values within their range exactly, while floating point types almost always give only an approximation to the correct value, albeit across a much larger range. The three floating point types differ in how much space they use. 32, 64, or 80 bits on x86 CPUs, possibly different amounts on other machines, and thus how much precision they provide. Most math library routines expect and return doubles. Sign is declared as double, sign double, but there are usually float versions as well. Float, sign F float. Floating point basics. The core ideal of floating point representations, as opposed to fixed point representations as used by, say, ints, is that a number x is written as m times b underscore e, where m is a mantissa, or a fractional part, b is a base, and e as an exponent. On modern computers, the base is always 2, and for most floating point representations, the mantissa will be scaled to be between 1 and b. This is done by adjusting the exponent. Example, 1 equals 1 times 2, and the mantissa is 1 is the mantissa, I suppose. 2 is the base, and 0 is the exponent. 2 equals 1 is the mantissa. Okay. 0.035. 1.5 is the mantissa. 2 is the base, and the exponent is -2. The mantissa is usually represented in base 2 as a binary fraction. So in a very low precision format, 1 would be 1.000 times 2 to the 0. 2 would be 1.000 times 2 to the 1, and 0.375 equals 3 over 8 would be 1.100 times 2 to the -2. Well, the first 1 after the decimal point counts as a half, the second as a quarter, etc. Note that for a properly scaled or normalized floating point number in base 2, the digit before the decimal point is always 1. For this reason, it is usually dropped to save space, although this requires a special representation for 0. Negative values are typically handled by adding a sign bit, that is, 0 for positive numbers and 1 for negative numbers. Floating point constants. Any number that has a decimal point in it will be interpreted by the compiler as a floating point number. Note that you have to put at least one digit after the decimal point: 2.0, 3.75, -12.6112. You can specify a floating point number in scientific notation using e for the base 10 exponent. 6.022 e to the 23. Operators. Floating point types in C support most of the same arithmetic and relational operators as integer types. X is greater than y, x divided by y, x plus y all makes sense when x and y are floats. If you mix two different floating point types together, the less precise one will be extended to match the precision of the more precise one. This also works if you mix integer and floating point types, as in 2 divided by 3.0. Unlike integer division, floating point division does not discard the fractional part, although it may produce round-off error. 2.0 divided by 3.0 gives 0.666666663, which is not quite exact. Be careful about accidentally using integer division when you mean to use floating point division. 2 divided by 3 is 0. Cast can be used to convert integer values to floating point values to force floating point division. See below. Some operators that work on integers will not work on floating point types. These are Modello, use fmod from the math library if you really need to get a floating point remainder, and all of the bitwise operators. Not, left shift, right shift, and XOR and OR. Conversion to and from integer types. Mixed uses of floating point integer types will convert the integers to floating point. So 1 divided by 2.0 will give 0.5. You can convert floating point numbers to and from integer types explicitly using cast. A typical use might be this. Okay, let's use this as an example. So we'll just find a file, go to C, we'll make a new chapter. We'll call it chapter 8. And then we'll find in there chapter 8. Let's see. Cast.c maybe? Okay, we'll include stio.h, even there. Return an average of a list. Double average in some. Int in. Let me do my own. Okay, so we'll do int main void. We'll do, let's say, int first equals 1. And then float 2 equals 2.0. Okay. Float result, or I can just print that, right? Printf percent d percent n, and then we could do first divided by 2. Return 0. Oops. Get those better. So printf there? Nothing to be done. Warning. Let's type double. How do I? It's double. I don't remember what. Yeah, no. Where is my? Um, 'Let's look at my notes here. Not during reference. Where is the? That. Format specifiers. Format. Nope. The format specifiers. D for signed. Percent F? Is that's it? Just percent F? Okay. There we go. And compile. Point 50000 Very interesting. Okay. Well, we could have also done. We can convert floating point to explicitly using cast. You can find floating point numbers to and from integer types. Term double sum divided by n. Okay. So then if I said int 3 equals 3, and then I could do print explicit cast. Explicit cast to percent. What is double? Double. LF? Long double LF? Okay. LF. And then we'll do 1. Let's do double first by 3. Oh. There we go. And we'll run it now. And aha. So it did. If I didn't, and if I hadn't done the cast, print F without cast, it would be %d. And then it would just be first divided by 3. File. Okay, compile. There we go. Let me add some in. In. Make okay. There we go. Okay, there we go. So, what we have here is the first one is using float, and you get 0.5500. Second, using the explicit casting double to 2 ints, and you get 0.3333. And if we did it without the cast, we truncate the integer portion of it, and you get 0. Nice. Okay. So let's continue at this location. If we didn't put in the double to convert sum to a double, we'd end up doing integer division, which would truncate the fractional part of our average. Note that cast bind tighter than arithmetic operations, so the double applies to just sum and not the whole expression sum divided by n. In the other direction, we can write int I equals int f to convert a float f to int. This conversion loses information by throwing away the fractional part at f. If s was 3.2, I would end up being 3. The math library contains a pile of functions for converting values of type double to integer values of type double that give more control over the rounding. See, for example, the description of floor, sill, round, truncate, and nearby int in the GNU libc reference manual. The IEEE 754 floating point standard. C does not require specific implementation of floating point numbers, but unless you are running on very old or very odd hardware, you will probably find that float, double, and long double types are represented using the IEEE 754 floating point standard. The standard is designed so that floating point operations generally behave the way one would expect. This means that for most applications, you don't need to know the details of the representation, but it is worth knowing about limits on accuracy of results and about some extra floating point values provided by IEEE 754, like NaN, not a number, or INF, positive infinity. IEEE 754 defines several standard representations of floating point numbers, all of which have the following basic pattern. The specific layout here is for a 32-bit float. So we have a table of the bits and then the numbers. Bit. I'm not sure this table is. Let me make this big for a minute. Nope, that didn't help. Huh. I wasn't sure if that table was looking correct, so I'm not quite sure how to read this. Bit S. The bit numbers are counting from the least significant bit. The first bit is the sign 0 for positive. I see, okay. 1 for negative. The following 8 bits are the exponent in XS 127 binary notation. This means that the binary pattern 0, 1, 1, 1, 1, 1, 1, 1 equals 127 represent an exponent of 0. 10 million equals 128 represents 1, 0, 0, 0, 0, 128 represents 1, 0, 1, 1, 1, 1, 1, 0, equals 126 represents -1, and so forth. The mantissa fits in the remaining 24 bits, with its leading one stripped off as described above. Certain numbers have special representation. Because 0 cannot be represented in the standard form, there is no 1 before the decimal point, which it is given the special representation. 0 cannot be represented in standard form. There is no 1 before the decimal point. It is given the special representation of this long list of zeros. There is also a negative 0 equals 1, and then all of the zeros after that, which looks equal to plus 0 but prints differently. Numbers with exponents of 1, 1, 1, 1, 1, 1, 1 equals 255 equals 2128 represent non-numeric quantities such as not a number, returned by operations like 0 divided 0 dash 0 divided by 0 dash 0, and positive or negative infinity. A table of some floating point numbers generated by the program float.c is given below. And then we have a table here of some numbers and their representation in with mantissas, and then their bit representation as well. Interesting. Okay. What this means in practice is that a 32-bit floating point value, example a float, can represent any number between 1.17549435 e to the negative 38 and 3.40282347 e to the 38, where the e separates the base 10 exponent. Operations that would create a smaller value will underflow to 0. Slowly, IEEE 54 allows denormalized floating point numbers with reduced precision for very small values. And operations that would create a larger value will produce INF or negative INF, so positive infinity or negative infinity instead. For a 64-bit double, the size of both the exponent and mantissa are larger. This gives a range from 1.79769313486235157 e to the 308 to 2.22507385850720014 e to the 308, with similar behavior on underflow and overflow. Intel processors internally use an even larger 80-bit floating point format for all operations. Unless you declare your variables as long double, this should not be visible to you from C, except that some operations that might otherwise produce overflow errors will not do so, provided all the variables involved sit in registers, typically the case only for local variables and function parameters. So that was a mouthful. I think that if I get into the point where I need to use very high precision within floating point numbers, I will need to revisit this IEEE 754 standard here. Round off error. In general, floating point numbers are not exact. They are likely to contain round off error because of the truncation of the mantissa to a fixed number of bits. This is particularly noticeable for large values. Example, 1 e to the 12 in the table above. 1 e to the 12, okay. 999999954. Yeah, that's with the round off error. But can also be seen in fractions with values that aren't powers of 2 in the denominators. Example, 0.1. Oh, yeah. Oh, wow, yeah. Okay. Round-off error is often invisible with the default float output format, since they produce fewer digits than are stored internally, but can accumulate over time, particularly if you subtract floating point quantities with values that are close. This wipes out the mantissa without wiping out the error, making the error much larger relative to the number that remains. The easiest way to avoid accumulating error is to use high precision floating point numbers. This means using double instead of float. On modern CPUs, there is little to no time penalty for doing so, although storing doubles instead of floats will take twice as much space in memory. Aha. So it depends on the precision that you need, because these are, the round off error changes though too, doesn't it? Very interesting. It gets, why is it shorter? 4.8. Note that a consequence of the internal structure of IEEE 754 floating point numbers is that small integers and fractions with small numerators and power of 2 denominators can be represented exactly. Indeed, the IEEE 54 standard carefully defines floating point operations so that arithmetic on such exact integers will give the same answers as integer arithmetic would, except of course for division that produces a remainder. This fact can sometimes be exploited to get higher precision on integer values than is available from the standard integer types. For example, a double can represent any integer between -253 and 253 exactly, which is a much wider range from the values 2 minus 31 to 231 minus 1 that fit in a 32-bit int or long. A 64-bit long does better, so double should be considered for applications where large precise integers are needed, such as calculating the net worth in pennies of a billionaire. One consequence of round-off error is that it is very difficult to test floating point numbers for equality unless you are sure you have an exact value. As described above. It is generally not the case, for example, that 0.1 plus 0.1 plus 0.1 is equal to 0.3 in C. This can produce odd results if you try writing something like 4f equals 0.1, f is less than 0.3, f plus or equal. It will be hard to predict in advance whether the loop body will be executed with f equals 0.3 or not. Even more clarity ensues if you write 4f equals 0.0, f is not equal to 0.3, f plus equals 0.1, which after not quite hitting 0.3 exactly keeps looping for much longer than I am willing to wait to see it stop, but which I suspect will eventually converge to some constant value of f large enough that adding 0.1 to it has no effect. Most of the time when you are tempted to test floats for equality, you are better off testing if one lies within a small distance from the other. Example, by testing epsilons. Delta epsilons. Fab x minus y is less than or equal to fabs epsilon times y, where epsilon is usually some application-dependent tolerance. This isn't quite the same as equality. For example, it isn't transitive, but it's usually closer to what you want. So yeah, we remember that from like definitions of limit, right? If you're taking calculus, we use epsilons in the proof for a definition of a limit. Reading and writing. Matter of fact, let's look at it real quick. Definition of a limit. Where is it? There exists some. Yeah, let x be defined for all x not equal to a over an open interval containing an a. Let L be a real number. Then the limit as x approaches a of f of x equals L. If for every epsilon greater than 0, there exists a delta greater than 0, such that if 0 is less than the absolute value of x minus a, which is less than delta, then the absolute value of x of L, f of x minus the limit, is less than the epsilon. So saying that as you get closer and closer and closer and closer to 0 for some epsilon, you're going to converge onto this point of this limit. Okay. Reading and writing floating point numbers. Any numeric constant in a C program that contains a decimal point is treated as a double by default. You can also use E or E to add a base 10 exponent. See the table for some examples of this. If you want to insist that a constant value is a float for some reason, you can append f on the end, as in 1.0f. Oh. But what about the little f? Is that... Oh, it's a big F. Or is it just I don't know. For I/O, floating point values are most easily read and written using scanf and its relative fscanf and sscanf and printf. For printf, there is an elaborate variety of floating point format codes. The easiest way to find out what these do is experiment with them. For scanf, pretty much the only two codes you need are %lf, which reads a double value into a double pointer, and %f, which reads a float value into a float pointer. Both these formats are exactly the same in printf, since a float is promoted to a double before being passed as an argument to printf, or any other function that doesn't declare the type of its arguments. But you have to be careful with the arguments to scanf, or you will get odd results, as only 4 bytes of your 8-byte double are filled in, or even worse, 8 bytes of your 4-byte float are. Right, so then you have some truncation in that case. Non-finite numbers in C. The values NaN, INF, and so positive infinity and negative infinity can't be written in this form as floating point constants in a C program. But printf will generate them, and scanf seems to recognize them. With some machines and compilers, you may be able to use the macros infinity and nan from math.h to generate non-finite quantities. The macros is infinity and is nan can be used to detect such quantities if they occur. Interesting. Okay. The math library. See also the KNR Appendix B4. Many mathematical functions on floating point values are not linked into C programs by default, but can be obtained by linking in the math library. Examples would be the trigonometric functions sine, cosine, and tangent, plus more exotic ones. Square root for taking square roots, power for exponentation, log and exponent for base E logs and exponents, and f mod for when you really want to write x remainder y, but one or both variables is a double. The standard math library functions all take doubles as arguments and return double values. Most implementations also provide some extra functions with similar names. Example, sinf that uses floats instead. For applications where space or speed is more important than accuracy, there are 2 parts to using the math library. The first is to include the line include math.h. So you have the header file so that the preprocessor can link it. Somewhere at the top of your source file, this tells the preprocessor to paste in declarations of the math library found in math. The second step is to link to the math library when you compile. This is done by passing the flag -1m or lm to GCC after your program's source file. A typical command might be GCC minus. If you don't do this, you will get errors from compiler about missing functions. The reason is that math library is not linked in by default, since for many system programs it's not needed. Okay, so let us get some info on the math library. Oh, it's not there. Let's get some info on GCC though. And then I want to see where LM was. Okay. Info GCC. And then let's do -LM. I don't know what the -LM does. Language options? Not sure why they're saying that. Is that a 1M? Maybe that's a 1M. Info GCC 1M? There's no way. Oh. No, yeah, there's no, that's... Man, GCC 1M. That's LM. Oh, GCC. Man, GCC. L. I don't even see an L on there. Alf. Okay, let's Google then. I always try to use the documentation. If I can't find it, then I Google. GCC minus LM flag. Yeah, it's not there. It's not there. Linker options. Library? Okay. Oh, I should have looked at those separately. Yeah, that makes sense. My bad. Okay, let's go back there then. Okay, so we'll have minus L. A lot. Linker options. There we go. Boop, 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 boop. Minus L is library. What is minus M? Minus L is library. What is minus M? We're looking for minus M around here, folks. Minus M. Oh, reject. Let's do the beginning and minus L. Minus M. M, no. Association, math. Preprocessor. Include file. Wait, no. Include file. What? Hey, chat, do you know what does minus M mean? Yeah, option. Or in GCC flags. No. Link with shared library. Link will append the name. Oh. So is M short for math? LM. The errors from Kyler about missing the reasons the math library is not linked by default. Okay, so okay. Let's go to next chapter. Operator precedence in C, chapter 9. Operator precedence in C controls the interpretation of ambiguous expressions like 2 plus 3 times 4, which could in principle be parsed either as 2 plus the product of 3 times 4, the right way, or the summation of 2 plus 3 times 4, the cheap calculator way. For the most part, C parses unparenthesized expressions the right way, but if you are not sure what it will do with an expression, you can always put it in parentheses to force it to do the right thing. That makes sense. There is a table on page 53 of Kernighan and Ritchie that shows the precedence of all operators in C, which we reproduce below. The interpretation of this table is that higher entries bind tighter than lower ones. So the fact that multiplication has higher precedence than plus and both have higher precedence than greater than means that 2 plus 3 times 4 greater than 5 gets parsed as the product of 3 times 4 added to 2 is greater than 5. Associativity controls how an expression with multiple operators of the same precedence is interpreted. The fact that plus and negative associate left to right means that the expression 2 plus 3 minus 4 minus 5 is interpreted as 2 plus 3 minus 4 from that minus 5. The leftmost operation is done first. Urinary operators, ternary, and assignment operators are the only ones that associate right to left. For assignment operators, this is so x equals y equals 0 is interpreted as x equals y equals 0, assigning 0 to both x and y, and not x equals y equals 0, which would give an error because x equals y isn't something you can assign to. For urinary operators, this mostly affects expressions like multiplication p plus plus, which is equivalent to multiplication p plus plus. Increment the pointer first, then dereference it rather than increment the thing that points to p, that p points to. Function calls and indexing, urinary operators, multiplication, division, addition, subtraction, shifts, inequalities, equality, bitwise, and, or, XOR, or, and, or, ternary associates right to left, assignment associate right to left, and commas. Okay, that's pretty boilerplate, I guess, with other languages, I believe. Go to the next. Variables. So we're on chapter 10 now. Variables in C. We have memory, variables as names, variable declarations, variable names, using variables, initialization, storage class qualifiers, scope and extent, marking variables as constant, and pointers to constant. Variables in C are a direct extraction of physical memory locations. To understand how variables work, it helps to start by understanding how computer memory works. Makes sense. Understand variables, we need to understand how computer memory works. Memory. Memory consists of many bytes of storage, each of which has an address, which is itself a sequence of bits. Though the actual memory architecture of a modern computer is complex, from the point of view of a C program, we can think of as simply a large address space that the CPU can store things in and load things from, provided it can supply an address to the memory. That, again, guys, is why I'm learning C in the first place, because of the way C kind of looks at these things, these lower level concepts, really at the basis level, which I don't get with C# unless you use like unsafe code, and I don't get with Python. So this whole point of being able to directly affect memory is kind of what I'm a little bit excited about, and the reason I'm kind of taking this C programming journey. Variables as names. A variable is a name given in a program for some region of memory. Each variable has a type, which tells the compiler how big the region of memory corresponding to it is and how to treat the bits stored in that region when performing various kinds of operations. Example, integer variables are added together by very different circuitry than floating point variables, even though both represent numbers as bits. In modern programming languages, a variable also has a scope, a limit on where the name is meaningful, which allows the same name to be used for different variables in different parts of the program, and an extent, the duration of the variable's existing, controlling when the program allocates and deallocates space for it. So a variable has a scope and an extent. Okay. So the scope, I understand. I talk about scope a lot. Scope is something that's relevant in JavaScript and in Python and C#, and in other languages. Then extent is something that, I mean, I know we have garbage collection in Python, we have garbage collection in C#, in Java, in JavaScript, of course. but the extent of it is not something I usually control. So this is nice. Variable declarations. Before you can use a variable in C, you must declare it. Variable declarations show up in 3 places. Outside a function, these declarations declare global variables that are visible throughout the program, i.e. they have global scope. Use of global variables is almost always a mistake. In the argument list in the header of a function, these variables are parameters to the function. They are only visible inside the function body. Local scope exist only from when the function is called to when the function returns. Bounded extent. Note that this is different from what happens in some garbage collected languages like Scheme, and get their initial values from the arguments to the function when it is called. Okay, let's revisit that one. And outside of function, in the argument list in the header of a function, these variables are parameters to the function. Yes. They are only visible inside the function body, exist only from when the function is called to when the function returns. Bounded extent. Note that this is different from what happens in some garbage collected languages like Scheme. And they get their initial values from the arguments of the function when it's called. Excuse me. That makes sense. Yeah. Yeah, absolutely. So, what is that keyword in C that lets you set the kind of the life of the variable, but it's not exactly, because things on the stack, right? My understanding as I'm learning this is things on the stack, which is like the functions and stuff, those are automatically deallocated and allocated when they're declared and deallocated when their scope goes out. It's things in the heap that you have to use your memory allocation and the pointers and stuff that we're going to learn about later for. But there's a keyword that I recently learned, and I can't put my finger around it right now. I don't want to just say it without thinking about it, and I don't want to search for it. It's not local. Is it local? I was talking to ChatGPT about it a few nights ago. No. Automatic. Automatic. Okay. Inside a function. Before C99, only the start of a block delimited by curly braces. Such variables are visible inside a function. Before C99, only at the start of a block delimited by curly braces. Such variables are visible only within the block in which they are declared. Local scope again exists only when the containing function is active. Bounded extent. The convention that C has generally been to declare all such local variables at the top of a function. This is different from the convention in C++ or Java, which encourage variables to be declared when they are first used. This convention may be less strong in C99 code, since C99 adopts the C++ rule of allowing variables to be declared anywhere, which can be particularly useful for index variables and for loops. Yeah, that makes sense. Another feature of function parameters and local variables is that if a function is called more than once, even if the function calls itself, we're going to call that recursion. I do that functional programming. We'll do some recursion there. This is going to be fun to do some recursion when we get to that. Is there a chapter on recursion? Yeah, right here, recursion. Very interesting. Okay. Each copy of the function. Oh, what happened? It looks like... Can you guys still see? It looks like my stream might have dropped. It says that I was disconnected for some reason. But I see excellent connection up here. So I got a weird OBS error around 55. I'll have to check that once this is published. Okay. Okay. Let's so another feature of function parameters and local variables is that if a function is called more than once, even if a function calls itself, each copy of the function gets its own local variables. Variable declarations consist of a type name followed by one or more variable names separated by commas and terminated by a semicolon, except in argument list where each declaration is terminated by a comma. I personally find it easiest to declare variables one per line to simplify documenting them. It is also possible for global and local variables, but not function arguments, to assign an initial value to a variable by putting in something like equals 0 after the variable names. It is good practice to put a comment after each variable declaration explains what the variable does, with the possible exception for conventionally named loop variables like I or j in short functions. Below is an example of a program with some variable declarations in it. So that's a term of contention in the programming world. Some debate is commenting or not commenting. I seem to agree with the author here that okay, the antagonist side of the not commenting is that it just gives you another point of your code where you have to keep track of changes and those that after you that come work on your code. So like if I was down here and I put like a comment that says this is so that we can, I don't know, variable used to demo explicit and non-explicit cast. If someone comes in after me and does any code changes or work on this particular piece of code, they're going to have to, if they change that variable, they're going to have to change the comment as well. But that just, to me, is another point of the program where you should be doing something like that in the first place. It shouldn't be a reason not to do it, because you have to maintain a little bit more. Because in the long run, I think that the greatest amount of cost that an organization has is the cost of dealing with technical debt due to misunderstanding about how code works and introducing bugs because something was done without the understanding of what the existing code base actually did. So I agree with this, that putting some comments in, a little bit of comments to tell you what the program is doing, and then some comments to tell you like what these particular variables are for. It makes sense. I'm not against it. I think it's a good idea. Variable names. C is pretty generous about what you can use in variable names. Generally, any sequence of digits, letters, and the underscore character can be used, so long as the first character is not a digit. Very old versions of C may limit the length of external variables, those that can be referenced from other files, like library routines, to 6 characters, but modern versions don't do that. This explains the compact form of many standard library routine names, like malloc, printf, or stringlang. That makes sense. That makes sense, because you have 6 characters on each one of these. That makes sense. That makes sense. Older languages are more restrictive, and variable names have evolved over the years. So 110101001001001 physical addresses represented as bits. Hashtag FC27 typical assembly language addresses represented in hexadecimal to save typing. And because it's easier for humans to distinguish hashtag A7 from B6 than to distinguish this binary from this binary. That's true. I mean, I'm not there yet. A1 $, a string variable in BASIC. Back in the old days where BASIC variables were one uppercase letter, optionally followed by a number, optionally followed by $, for a string variable, and % for a integer. These type tags were used because BASIC interpreters didn't have a mechanism for declaring variable types. IFNXG7, a typical Fortran variable name. Back in the days of 6-character all-cap variable names, the I at the start means it was an integer variable. The rest of the letters probably abbreviate some much longer description of what the variable means. The default type based on the first letter was used because Fortran programmers were lazy, but it could be overridden by an explicit declaration. So this is some integer for function G. That's crazy. IJC count top of stack, accumulated time in flight. Typical names for modern C programs. There is no type information contained in the name. The type is specified in the declaration and remembered by the compiler elsewhere. Note that there are two different conventions for representing multi-word names. The first is to replace space with underscores, snake case, and the second is to capitalize the first letter of each word after the first. You should pick one of these two conventions and stick to it. But which one do I pick? Which one do I pick? Which one? Let's see. Should I use snake case or camel case in C programs? Consistency, yeah. Oh, you could use the GDK. So that's a good idea. That's a good thing to do sometimes, is if you're unsure what kind of style to use and you're learning a new language, you can look up the style for the language that, like, a large project that language is using. So for, like, instance, this one, C, we might look at, like they said, GDK. So we could look at GDK style guide. No. Developers. Design guide. There we go. Design principles, guidelines, patterns. No. GDK code style guide. Code style guide. Coding style. There we go. C programs and no. So line width, we're saying 80 and 120. Okay. Indentation, we're doing the curly braces on the first line with the space in between them. And then the naming. Where is my naming? Functions should be declared by placing a return value on a separate line from the function name. Really? Why is that? Very interesting. So like this? Int. And then below that is, I guess, I don't know. I don't know if I'm in love with that. Okay. An example of Hungarian notation, PRC grade note database. An example of Hungarian notation, a style of variable naming in which the type of the variable is encoded in the first few characters. The type is now back in the variable name again. This is not enforced by the compiler, even though I number of students is supposed to be an int. There is nothing to prevent you from declaring float I number of students. If you are teaching a class on improper chainsaw handling and want to allow for the possibility of fractional students, see this MSDN page for much more detailed explanation of the system. Not clearly an improvement in standard naming convention, but it is popular in some programming shops. In C, variable names are called identifiers. These are also used to identify things that are not variables, like functions and user-defined types. Let us end variable names. We'll go over that section again. We'll call it here for today. We've made some good progress. So we'll pick up on chapter 10, variable names, on our next stream. I'm seeing that a few more people have subscribed to these streams. If you guys have any questions or comments, please put them under the video, and I'll try to answer them on the next streams. Again, I know this is kind of a chaotic process of this stream, and again, the number one reason for it is I'm using this as a log of like my learning journey. But if it's helping anybody out and y'all want to join me along for that journey, feel free to subscribe. I plan on doing a couple cool C projects once we have a bigger grasp of the language. That'll be it for today, though. Thanks for joining in, Keen and Can Do. And until next time, we'll see you later.